So 2.6, a parent function is the simplest form in a set of functions that forms a family. So each function in the family is a transformation of the parent function, which is crazy to think about. Any graph you can think of is actually going to be rooted back to one of these parent functions. A blank shifts the graph of the parent function, so a translation, back to some geometry terms here, a translation is a shift. It shifts the graph of the parent function horizontally, that's left and right, or vertically, or both, without changing the shape or the orientation. So you can see this first graph is a representation of a vertical translation, and you can see you have the parent function here in the middle, and then the vertical shift upwards is adding k, so is and then the shift downwards is a minus k, but in general we have f of x plus k is a vertical translation. Here with the horizontal translation, you'll notice that the h is inside the parentheses, so that's a horizontal translation. And interesting to note that when we shift to the left from our parent function, it's actually a plus h, so it's opposite what you would think. When it says x minus h, that's a shift to the right. Similar to what we experienced with the point slope form of the line, where we had to plug in the x1, y1, and it was opposite what we thought it would be.
Is this like really complicated?
Yeah.
Or is it just like pretty simple?
Pretty simple. Yeah, we'll see some examples here will make it a little bit clearer. So, how are the functions y equals x? Should immediately come to mind, oh yeah, that's the one that's a straight line through the origin with a slope of 1. That's the parent function of all lines. So plot that line on that graph. I made the graphs bigger this time for you so we can at least see the numbers.
Helpful.
Thanks. And then y equals x minus 2, hopefully that minus 2 reminds us it goes through, has a y-intercept of -2, but now we can also think of that as a shift downward of the line y equals x. Same slope, so it's not changing shape or changing slope at all, it's just shifted downwards 2 units. Now this next one, I'm going to share with you my song for parabolas. So if you think of this function here as our parent function parabola, but just shifted down 1, the key thing is noting where the vertex is. Once you can plot the vertex, the same song applies to all parabolas. It's called the parabola song. From this point, you go over 1, up 1, left 1, up 1, over 2, up 4, left 2, up 4,
Killer vocals.
parabola.
Killer vocals.
Thanks.
That was great.
My grandmother was a vocal teacher. I got started at a young age, so.
I'm a parabola.
I'm gonna get to sing this one more time. When we shift, translate this parabola up 5 units. So we're just gonna move the vertex up 5 units. However, when I made the graphs bigger, I didn't leave a whole lot of space up here, so it's gonna be a shortened version of the song. Over 1, up 1, left 1, up 1, parabola. That was, thanks for joining in on that one, thanks.
That's just too cute.
We kept that to be the choir.
That'd be the best ever. All right. The other notes on here indicate different types of transformations. So this first one is going to be talking about the vertical stretch versus the vertical compression. So you really have to look carefully here to figure out what the f of x function is referring to. And it's actually kind of like the middle one here. In color it's a little more obvious, but all of this is just indicating if we multiply our function by a constant where a is greater than 1, it's going to be a stretch. Okay? So you can see here's a times the function, and you can see that it stretched out versus a vertical compression here, and that's going to happen when your a value is between 0 and 1. Think of numbers between 0 and 1. You've got half, you've got a fourth, you've got 3/4, mainly fractions, right? We think of those as fractions. And you can see this guy that's closest to the x-axis, that curve, so it gets like fatter. So I think of the fractions in front make the graph fatter.
I think it's fatter with a PH.
Yeah. The last type of transformation we'll talk about then is reflections. Are reflections. And remember, a reflection is a flip. So here's your example. F of x is this dark one here in the first quadrant. When you reflect or flip over the x-axis, notice that the x values stay the same, but the y values are opposite, right? So it's still a 3, but there's, instead of a 4, it's a -4, and so on. And each of these, the whole graph is the same distance above the x-axis above as it is below, okay? And then reverse, when we reflect over the y-axis, the y values stay the same. So see how the 1 and the 1, they stay the same, but the x values become opposite.
So wait, can you repeat that one more time? You said that when you flip over the x-axis, the y stay the same, and when you flip over the y-axis, the x stay the same?
No, when you reflect over the x-axis, the x values stay the same, but the y values change signs. But when you reflect over the y-axis, here we go. When you reflect over the y-axis, the x values change signs, but the y values stay the same. So basically, the axis you flip over, those values stay the same. It's the other ones that become the opposite. And we can create function rules based around this pattern that we establish here, that reflecting over the y-axis, we are just going to take the opposite of each of our x values, versus in reflecting over the x-axis, we'll take the opposite of each of our y values from whatever the original equation was. And then here's a concept summary, which I really like. This is great to come back to as we go through the homework assignment and go, oh, what was I supposed to do? in order to get a stretch or a compression or reflection? How did that work out? Lastly, on the back here, reflecting a function algebraically. So, looking at this original function that we have, f of x equals 3x plus 3. And we're going to do a reflection in the y-axis. So this is the rule for doing a reflection in the y-axis. So, for our f function, we're going to plug in a negative x, okay? See that? That's the rule. It says plug in a negative x. When we plug in a negative x where there previously was a regular old x, what that's going to do is just change this first part, which is our slope, right? Our slope went from being a positive 3 to a negative 3. And notice, when we're doing that y-axis reflection, the y-intercept actually stayed the same, because that would be a particular y value. It's going to stay the same for those y-axis reflections. Okay, there's a couple of practice questions down there. We're going to go ahead and do some practice through our Math Excel assignment.